Uh, so, yeah, welcome back to this problem session for the course Introduction to Abstract and Linear Algebra. My name is Harshita. I'm a PhD student at ISET Tirupati. So, today we'll discuss some problems related to the content of week 6. So, we will start off with this question here. So, you have a linear transformation from R2 to R3, which is given by T of x1, x2 is x1 plus x2, x1 minus x2, and x2. So, the question is, what is rank of T? So, let's just recall what do you mean by rank of a transformation? And even before that, maybe we'll just check once that this is in fact a linear transformation. So what do we have? As of now, we have a function from R2 to R3, right? Where x1, x2 goes to x1 plus x2, x1 minus x2, and x2. So when does a function become a linear transformation? There are two conditions which it needs to satisfy. So recall, if you have T from some vector space to another is a linear transformation. First condition is T of u plus v should be T of u plus T of v. And second thing is, when you multiply with a scalar, the scalar comes out. So it becomes alpha times T of u. So, so we'll go back to the question. So we have x1, x2 going to x1 plus x2 and x1 minus x2 comma x2. So the question is this a linear transformation? Right? So let's check. So for the first condition, we'll take two vectors. Let's say u is u1, u2 and v is v1, v2 belongs to R2. We want to see if T of u plus v equal to T of u plus T of v. So let us first compute T of u plus v, which is nothing but T of u1 plus v1 comma u2 plus v2. So what is the map given by x1, x2 goes to x1 plus x2, x1 minus x2, x2. So here this whole thing is like a x1 and this whole thing is like a x2. So u1 plus u2 you can see it as x1 and u2 plus v2 you can see it as x2. So this will be x1 plus x2. So x1 minus what is it? x1 minus x2 So that is u1 plus v1 minus u2 minus v2, and finally the second coordinate as it is. So this we can write it as u1 plus u2 comma u1 minus u2 comma u2 plus the v terms. So v1 plus v2 v1 minus v2, and you'll see that this term, the first term you see is nothing but t of u1 u2, and the second term that you see is nothing but t of v1 v2. So this is t of u plus t of u. This verifies the first condition of the linear transformation. And second condition is when you multiply with an alpha. So t of alpha u. What is that? T of alpha u1 alpha u2, which is alpha u1 plus alpha u2 plus alpha u2. And here it's more direct. You can just take alpha common from the whole thing, and whatever is inside, you'll see that it is t of u. Okay, so although it was not asked, just wanted to brush up the concept of linear transformation. I hope this is okay. Any questions? Okay. Okay. If there are no more questions, let's go back to actually what we were asked to do. So we have this linear transformation, and the question is, what is the rank of t, right? So rank of t means the dimension of the image space. So rank of t basically means dimension of image of t. So what is image of t? It is nothing but everything of this form, right? x1 plus x2, x1 minus x2, x2, where x1, x2 are coming from real numbers. So we want to see what is the dimension of this space. Uh, so let us rewrite it in a slightly different way. We'll take the x1 terms separately and the x2 terms separately. So we can write it as x1 x1 0 plus x2 minus x2 x2, right? Now what is this? This is nothing but x1 times 1 1 0 plus x2 times 1 minus 1 1. So what is the image of t? You see that there are one vector and another vector, and you are actually looking at the span of these two vectors, right? What do you mean span of vectors? You take all combinations of those two vectors. So you can, if you recollect what is span, you can see that this is nothing but span of 1, 1, 0 and 1 minus 1, 1. Now, what is the dimension of a space spanned by vectors? You see, how many linearly independent vectors can you see use to span it? Like what I want to say is, okay. So, suppose we have span of, let's say, 1, 0, 0, 0, 1, 0 and 1, 1, 0. So although we are taking three vectors to span the space, we don't really need all of them because this third vector is actually contained in span of these two, the first two vectors, right? So in fact, this will be same as span of just the first two vectors because third vector is nothing but the sum of the first two vectors. So the dimension of the space will actually be 2 and not 3. Uh, I just want to mention this because although here that's not the case. So for us to make sure that we have two vectors, but what if we can span it with only one vector? We have to just check and see if these two vectors are linearly independent or not. So we can check that 1, 1, 0 and 1 minus 1, 1 are linearly independent. So the dimension of this space is actually 2, which is what we wanted. Dimension of image of T is 2, which is same as rank of T. Any questions so far?
If it is linearly dependent, in that case, what will happen?
In that case, you have to find a linearly independent set which spans the space. So what you can do is like here, this is an example where it was dependent. So these three were dependent. And because we can write the third vector as a linear combination of the first two, you remove the third vector. You have the same span. Now again you check, are these two vectors linearly independent? If that is so, then that will be the dimension. If not, you throw away one vector which can be written as a combination of the other vectors and you keep doing this.
Okay.
Yeah. Any more questions? Okay, I hope checking that this is independent is okay. We can come back to this if we have time. We'll move on to the next question. Which of the following statements are correct? So the
Is there
first,
any, ma'am, is there any other method to check to find out the rank of T by using matrix, etc.?
yeah, you can. Uh, So if you know how to find the rank of a matrix,
Yeah.
and also you know how to convert a transformation into a matrix,
Mm.
then you can write this transformation into the, so how to write it in terms of a matrix, there is a question, we'll look at it. And once you write it in the form of a matrix, you can, if you know how to find to determine the rank of the matrix, then that will be the same.
So can we solve these questions by using matrices?
Yeah,
By
you can do
converting
that
into
also.
matrix?
You can do that also. So there is one question where it, one of the questions it will come where we have to convert a linear transformation into a matrix. Maybe we'll try to find the rank also there.
Okay.
We can look at it. Okay. So which of the following statements are correct? The first statement says if U and V are two vector spaces over a field F and T is a linear transformation from U to V, then kernel and image are subspaces of V and U and V respectively. So I think this has already been proved in class. So I'll just say that it is true. The second statement says that you have two vector spaces and you have a linear transformation from U to V. If the dimension of U is finite, that is U is finite dimensional vector space, then dimension of U equal to dimension of kernel of T plus dimension of image of T. So even this, it is the rank nullity theorem which has been again done in class. So this is by rank nullity. The statement true is also right. Uh, the third one, if W is a proper subspace of a finite dimensional vector space V, then W is finite dimensional and dimension of W is less than dimension of V. So yeah, is this true?
Yes, ma'am, true. It is proper subspace, no?
Yeah. So since it says, so in general for any subspace, you can see that the dimension is less than or equal to dimension of V. But here, since it's a proper subspace, it is strictly less than dimension of V. So this also is a true statement. Okay. Any doubts here?
No.
Yeah, these are just statements. So okay. Uh, yeah. So this is an example where we see how to move from a linear transformation to a matrix. So yeah, let's see. Okay, so let T be a linear transformation defined by T of x comma y comma z is T of x y z is x plus y and y minus z. The matrix of T with respect to some ordered basis. So first of all, this is a map from R3 to R2, right? And whenever we see, when we say linear transformation, we're just given a formula T of x y z equal to something, and you substitute your values and you get your answers. But when we want to express the transformation as a matrix, we always do it with respect to some basis, right? We need a basis for both the codomain and the domain. Okay. So here domain is R3 and they have given this particular basis of R3. So I'll call it B1, 1, 1, 1, 1 minus 1, 0, 0, 1, 0. And the codomain basis has been given to be 1, 1 and 1, 0. Okay. So does anybody know how to get the matrix of a linear transformation?
You have to find out the transformation of basis.
Mm-hmm.
You have to find out TB1 and TB2.
Okay.
And then transport of that
What of that?
matrix. Transpose of the
Transpose.
matrix formed by the TB1 and TB2.
Okay. Vaguely okay, but does anybody want to make it more precise? Okay, first of all, is a TB1 and TB2. That is, see, B2 is are vectors in R2. So T is a map from R3 to R2. So T of B2 doesn't make sense.
Okay.
Yeah, but closely, you're right. Anybody wants to add something?
You have to find out T of 111, T of 1 minus 10, and T of 010.
Yeah, that's right. And then,
And then we have to form a matrix of that.
so how will we find that, form that matrix?
Rho will be will be that T of E1. So suppose that is E1, E2, E3. If you consider 111 and that is E1, E2, E3, then
Mm-hmm.
you have to find out T E1, T E2,
Mm-hmm.
and T E3.
Mm-hmm.
Then whatever we get, that has to be converted into matrix form.
Yeah.
And then
So,
we have to find out that transpose of that matrix, whatever we get.
okay. Right. So, one point I would like to add is, so what you said was right. You find T of 111, but once you find T of 111, how do you move to the matrix form is, whatever value you get, you have to write that as a linear combination of B2. Otherwise, there should be some reason why B2 is also given, right? It's with
Okay,
respect to both the bases. Yeah, that's the only change. Otherwise, it was fine.
okay.
So we'll do that. Let's first find out what is T of 111. So it is x plus y minus z, right? So that will be 1 plus 1, 1 minus 1, which is 2, 0. Okay. Then T of 1 minus 1, 0. This is 1 plus minus 1 minus 1 minus 0, which is 0 minus 1. Then T of the third vector is 0 plus 1, 1 minus 0, which is 1 comma 1. Okay, so this is done. Now the task is, what all the answers that we get, we write it as linear combination of the other basis vectors or the basis that we have of the codomain. So 2, 0, you want to write it as sum a times 1, 1 plus b times 1, 0. We can calculate it, but is there any direct guess for the values of a and b just by looking at it?
A equal to 0, no?
Yeah. So you see that 2, 0 is nothing but multiple of 1, 0. So Basically, here you don't even need to compute. It is 0 times 1 1 plus 2 times 1 0. Okay. So 0 minus 1, what would this be? So something times 1 1 plus something else times 1 0. Can you try it out and let me know? Okay, so I'll write out the equations and solve it, but here it is not so easy to make a guess without really solving it. So how do you solve it? This is nothing but a plus b and a. So what does that give? A plus b equal to 0 and a equal to minus 1, which will give b equal to 1, right? So 0 minus 1 is nothing but minus 1 times 1 comma 1 plus 1 times 1 0. Okay, and finally the last one is 1 1. Oh, mm, yeah. Okay. Finally, 1 1, there's nothing to do. It is already there in the basis vector. So 1 times 1 1 plus 0 times 1 0.
कोण येते तुला एक्स्ट्रा मला माझा अभिषेकचा येते असं
Okay. So now, what are the coefficients that we have got? So this is t of the first basis vector 1 1 1. This is t of 1 minus 1 0. This is t of 0 1 0. Right? So what are the coefficients we have got? 0 2 minus 1 1 1 0. Right? Now, if you want to write the matrix of this transformation with respect to the basis, so what you do is, so I prefer to do it this way. You take the first basis vector, right, which was first basis vector of your domain, which is your 1 1 1. You find t of that, write it as a linear combination of the basis of the codomain. You look at the coefficients that you get, which in this case is maybe color coded. So 0 and 2, right? You write it as a column. Next you do the same thing. Take the second basis vector, write it as find t of that, write it as a linear combination of the basis of the codomain. Whatever coefficients you get, write it as your second column. Minus 1 1, and the same thing for your third basis vector. So the coefficients constitute your third column, right? So this is the matrix of the transformation with respect to the basis. And coming back to the question that came up while we were solving the first thing, how do you find rank of t? So either you can do it the way we did it, or if you get a matrix with respect to any basis, you can find rank of this matrix. So rank of t will be equal to rank of this matrix. And does anybody want to know how to find rank of a matrix? Whatever we used to do in school level, the same thing. but does anybody want a recap?
Yes, ma'am. Just a recap.
Okay, so one easiest way is you convert it into echelon form. So how do you find rank of a matrix? So first thing is you convert to echelon form. You can use row or column transformations, but let's just stick to one using row transformations. After you convert it, you just count the number of non-zero rows. Okay, and what is echelon form? Mm, yeah, so echelon form is uh, you may find slightly different versions in different textbooks, but for our purpose, all we need is that the lower triangle should be 0. So you can have some entries here. So for our purpose, this much is enough. Sometimes they insist that each of these entries should be 1 and things like that. But anyway, for finding the rank of a matrix, it doesn't matter. So let's do one example. Let's do this example itself. 0 minus 1, 1, 2, 1, 0. So 0 minus 1, 1, 2, 1, 0. So here the lower triangle is just basically just one entry. This is the lower triangle which we want to make 0. So we'll do some row transformations. Here the first option is to switch row 1 and row 2. You interchange row 1 and row 2. What do we get? 2, 1, 0, 0 minus 1, 1. So we got the lower block 0. Now you just count the number of non-zero rows. We have two non-zero rows, right? So the rank of this matrix is 2. So maybe we'll look at one more example. Okay. So if we look at this example, what is the lower block? This block, right? So our task is to do some row operations to make all of these entries 0. So this second row first column entry is already 0. We'll try to make the first two entries in the third row 0. Right? So what will we do? First thing we can do row 3 minus row 1. So you subtract row 1 from row 3. This becomes 0. 3 minus 2, 1. 2 minus 1, 1. Now we want to make this entry also 0. So what will we do? Subtract row 2 from row 3. So when we do that, in the process what is happening? The entire row is becoming 0. Right? So you see that there are only two non-zero rows after you have converted to an upper triangular matrix. So the rank of this matrix is 2. this okay?
Yes, ma'am, correct.
So, as somebody brought it up, even in the first question where we found the rank, we did it theoretically by looking at the image space. So, what you can do is take any basis. So, you can try this now. You take some standard basis. So, you take usual, it's a map from R2 to R3. You take the usual 1, 0, 0, 1. So, let me write it here. Take B1 is 1, 0, 0, 1. It's a basis of R2. You have a basis of R3. Now, just like how we got the matrix there, you try to get the matrix of the linear transformation here. Then you try to find the rank, and you see that the rank should turn out to be whatever we got here. So both ways it is fine. Any questions so far?
No.
Okay. Okay. So here you have the next question, the transformation T from R3 to R2 defined by T of x comma y comma z is equal to x plus y, x and y plus z. So is this a linear map, and what about its kernel? Okay, so linear, we'll check that. You have T from R3 to R2. XYZ goes to x plus y, y plus z. Is it linear? Again, we have to check the two conditions. So let's take two vectors. U is say x1, y1, z1, and v x2, y2, z2. So what is T of u plus v? T of x1 plus x2 So this is given by x plus y, which is x1 plus x2 plus y1 plus y2. This is the x coordinate and this is the y coordinate, comma y plus z. Yes. Right. Again, we can just split it up. So we can write this as x1 plus y1 plus x2 plus y2, comma y1 plus z1 plus y2 plus z2, which is equal to x1 plus y1, y1 plus z1 plus x2 plus y2, comma y2 plus z2. See, there is nothing much that we are doing here. We are just factually writing it so that we get t of u plus v equal to t of u plus t of v. If you find this difficult, you can compute t of u plus v, t of u plus t of v separately and verify that both are same. That is also fine. Next, we will verify t of alpha u. So this will be t of alpha x1, alpha y1, alpha z1, and this is alpha x1 plus alpha y1, alpha y1 plus alpha z1. So you can take alpha common. So this is what we get, and whatever is in the bracket is nothing but t of u. So t is in fact linear. Okay. The next part is, what about its kernel? Will it be 0 or will it contain a non-zero vector? We will do the computation, but can you answer it just by looking at it or using something that you have learned in the class? Yeah. Okay, I'll give you a hint. Can you think about rank nullity theorem? Anybody wants to try? It's okay if it's not the right answer. You can just guess. Okay.
Rank of T will be T R2, no?
Rank of T will be
2.
2. Okay. So
So nullity is 1.
yeah, exactly.
Greater than 0.
So what does rank nullity theorem tell us? If you have, so you just recall rank nullity theorem. So what does it say? If you have a map from some vector space U to another vector space V, and assume that U is finite dimensional. So dimension of U equal to rank of T plus
Nullity.
nullity
Nullity
of,
of T.
yeah. So what is actually nullity of T? It is the dimension of kernel of T. Now you look at the map that we have. We have T from R3 to R2. Whatever the map is, x, y, z goes to x plus y, y plus z. So what is rank of T? It is a dimension of image of T. But the image of T is a subspace of R2. Right? So mm, rank of T equal to dimension of image of T, but image of T is actually a subspace of R2. So the dimension can be at most 2. Forget what it is here, but at most 2 is always less than or equal to 2. Now you will apply your rank nullity theorem. So rank nullity says that dimension of your domain, which is R3, equal to rank of T plus dimension of kernel T. So this is 3. Rank of T is a number less than or equal to 2 plus dimension of kernel T. Now you take this 2 this side. So what we get is dimension of kernel of T is greater than or equal to 1. So it doesn't matter what your transformation is. Why did this happen? Because this image of T is lying in a space whose dimension is less than the domain, right? Because we have a 3 here and we have this 2 here, which is a smaller number than 3, this dimension of kernel of T is turning out to be something greater than or equal to 1. So we have actually shown something. So if you have a linear transformation from a vector space U to V, and if dimension of V is less than dimension of U, then T will always have a non-trivial kernel. That is, dimension of kernel of T will always be greater than 1, or the kernel cannot be just singleton 0, or the map cannot be a one-to-one map. Is this okay? So, is there any questions? We will in
Oh,
fact
ma'am, that inequality is sign. Can you repeat that?
here. Okay, is this okay? The dimension, see, image is a subspace of R2, right? Uh,
Yes, ma'am. Right.
so, dimension of the image is less than or equal to 2. This is nothing but your rank of T. So, rank of T is less than or equal to 2. So, here where there is rank of T, we have substituted that it is less than or equal to 2. Is this okay?
Oh, yes, ma'am.
Yeah. Then you just take it to the other side. You take 2 to the other side, so you get
But that equality sign is there, no? Dimension of R3 equals to rank.
yeah, but this rank, we are just saying that it is less than or equal to 2. See, this is true, but we have a bound on the rank, right? This is like saying A is equal to B and B is less than or equal to C. So what can we say? A is less than or equal to C, right?
Hmm.
That's what we're saying. So here our A is dimension of R3, B is rank T plus nullity of T, and C is 2 plus nullity of T. Is that okay?
Okay, ma'am. Got it. Next.
Anybody has any questions? Okay. So Sorry?
Oh,
Okay. So, uh, just directly by using this rank nullity, we can say that it has a non-trivial kernel. But in fact, you can find what is the kernel also. So you're looking at all those vectors such that x plus y plus z gives 0. So let's actually get the kernel of D. Is all those x, y, z such that x plus y plus z equal to 0, comma 0, which is equal to x, y, z such that x plus y equal to 0 and y plus z equal to 0. So these are all vectors in R3. Right? So x plus y equal to 0, it just means that y is equal to minus x and z is equal to minus 5. But minus 5 is nothing but x.
X.
So it is vectors of the form you have x, y is minus x, z is x. So even if you don't use rank nullity, you can see that this is a one-dimensional space. Kernel D is a one-dimensional. So in fact, we have a verified rank nullity here. We can see that kernel is one-dimensional and the rank is two-dimensional. The rank is 2, so 2 plus 1 is 3. Is this okay?
Yes.
Okay. Okay, so we have one last question. Excuse me. So we have a linear transformation from R2 to R3 and we only know the value of the transformation at 2 points, which is 1, 1 and 2, 3. So how do you find it in general? So this is the one thing beautiful about linear transformation. All you need to know is what is the value of this transformation on any basis. And the way the linear transformation is defined, that if you take sum, it splits. If it takes scalar multiples, it gets multiplied and so on. You can actually determine what is the value of the transformation at any point. So here we just know the value of the transformation at 2 points, 1, 1 and 2, 3. So how do we get it at any random xy? What do we do?
So to substitute that figure in check.
Substitute. Okay. So suppose instead of any xy, suppose we say what is t of 2, 2. Then how would you find out? Just see. We know what is t of 1, 1 and what is 2, 2. Just twice of 1, 1, right? T of,
1 plus
yeah.
1.
Yeah, or you can see it as 1, 1 plus 1, 1. Either way. So this will just be 2 times t of 1, 1. Now if we say similarly, let's say t of uh, 3, 4. This is nothing but 3, 4 is nothing but 1, 1 plus 2, 3.
Hmm.
So now you know that this should be T of 1, 1 plus T of 2, 3. You know what is this value, you know what is this value, you can substitute. Now instead of going like these, one vector by vector, we want to see what is T of x comma y in general. So what does that mean? We have to see how do we write a general vector xy. Suppose we give you some xy, 5, 6, 7, 8, minus 5.3. Can you write it as some linear combination of 1, 1 and 2, 3? So all we know is what is the value of T of 1, 1 and what is the value of T of 2, 3. So can we in general write it, right? That is the task. So in other words, what we are saying is, given an xy, which linear combination works? Can we find A and B in terms of x and y and some numbers? So this is just solving some equations. Let this, and our task is to find A and B. So this would mean
A plus 2b. A plus 2b is equal to x.
yeah. So A plus 2B equal to x.
Yes, and a plus 3b is equal to y.
Now,
We have to write a and b in terms of x and y.
yes. So you can just subtract the first equation from second equation. What we get is B equal to y minus x. Right? And substituted any one of them. So let's say we substitute in 1. So what we get is A plus 2 times B is y minus x equal to x. So that is A plus 2y minus 2x equal to x. So just don't get confused because we are using x and y. Here we are
It's x
trying
and
to
2.
find what is A and B.
A and b.
So A,
X
B.
minus y.
So what this means is you take any xy, it can be written as 3x minus 2y times 1 1 plus y minus x times 2. So you can in fact just multiply and check if you wish. Now you know what to do. So what is T of xy? So when we say xy, we have these
X minus
values.
2y.
So this will be 3x minus 2y into T of 1 1 plus y minus x into T of 2 3. And these two values are something that we know. What is it? 102 and 1 minus 1 4. So 102 plus y minus x into 1 minus 1 4. Uh, if you multiply and add it up, what you'll get is, so you can check that this is what you get, just multiplication and addition. So this is a linear transformation in general. Yeah, we'll end with this unless there are any questions that you want to ask.